I'm Philip. I talk about databases. Thanks to sponsors for making the event possible. And as I've already been asked, I'm from Vienna. I'm always describing it like I'm from Vienna, a city of fatty foods, classical architecture, and beautiful women. No, we love Conchita. Finally, we won the Eurovision contest with her. I'm at Elastic. I'm part of the infrastructure team, so we do everything like testing with Jenkins, AWS instances, Ansible Chef, publish scripts. And this here is a pipe, and I kind of pipe my infrastructure work into developer advocacy. So I'm out in London at conferences and meetups just to talk about our stuff and other stuff I find interesting. And when I'm not running around somewhere in the world, back at home I always also run meetups. One about databases in general, and the other one about papers. So we meet once a month and talk about one classical computer paper. Sometimes distributed systems, sometimes old languages. We had just like Perl and Prolog and whatever, how different languages developed and stuff like that. Now we're more into machine learning. And this talk is kind of the combination of these two. So we'll start off with some theory. Try to keep it light so you don't fall asleep. And then we'll dive into a few specific database systems. Okay, so let's get down to databases. What are databases and how did we get here basically? Like the classical paper is a relational model of data for large shared data banks by Kod from I think 1970, which kind of founded how we see databases today. Like before that, you had different implementations of databases and everybody had their very own implementation, and if you wanted to interact with that, your application had to be just geared towards that database very specifically. So you couldn't switch anything. You really needed to know like how does this database work internally just to make use of it in an efficient fashion. And Kod said, well, this is stupid. Let's find something more intelligent. I will just generate a generic model like just the mathematical abstraction, and everybody can then use that, and then all the systems are kind of abstracted away, and nobody does need to care about these internals of the databases, which sounds very reasonable. And what Kod in the end gave us is a relational model and normal form, which led to the data independence. So you just have this mathematical model as the underlying idea, and everybody implements that, and that leads to some kind of data independence. You don't need to know how is the data actually stored and organized internally. You're just relying on the mathematical model. And what Kod did was this here. If you can read it, this is what we would use today, select name from people where dialect is null, so all the people that are still alive. This is not what Kod did. Kod did this. He created just a mathematical idea, and I guess most of us are pretty glad we don't need to interact with that. So he says we have a free variable name t with an attribute name, and there exists a tuple name and died age where this x that exists is in the sum of people, and the x died age is empty, and the t name matches that x, and that can kind of translate it down to that. So this is basically what Kod did. It was just a mathematical idea in the background how to interact with that. And then also IBM guys came up with SQL, a structured English theory language, by Boyce and Kod. Definitely not Boyce. And you can see this was SQL. Today we just have SQL because somebody else had the trademark on SQL. And they started with it, and then the company having the trademark complained, and then they said, well, we'll just remove a few letters. And afterwards it was then called, SQL, the acronym, actually the SQL was first, and then it was just stripped down to SQL. Yeah, and what that gave us is that is kind of declarative. We do not need to know how this works internally. We just tell it like, these are the rules and I want the stuff. That is how do you do that internally? I don't care. I don't care if this is a loop like for, while, do loop, I don't care. Just these are the rules, give me data fitting those rules. And the internals are then part of the query optimizers. So you do not need to know how MySQL does the SQL Server, Postgres, whatever. You don't care. That is thanks to Code's abstraction layer, that all of them behave kind of the same way. And you can also see this was already made for user interaction. Like you have aggregated reports back in the 80s when the relational databases started to come up. This was kind of a new thing that even untrained people could just write very simple SQL queries and get very powerful data back. Before that, you had to write your own programs and do complicated stuff. This made it much simpler. Like you have these aggregated reports where you can just do group by, sum, average, whatever. But what untrained users or even trained users are not so good at are normally stuff like concurrency, integrity, and stuff like that. That is why relational databases take care of that for you, and you don't need to care about that because that's also handled internally. And one other very nice thing Cod did was he wrote another paper, which he called Cod's 12 rules, which were actually 13 rules because like every good person in IT started counting at 0 and then went down to 12. And there he defined what are the rules, or what does the database need to do if it wants to be called a relational database. Because like there were all these vendors who had products out previously, and they would just add one tiny little feature to their database from the relational model and then say, oh, this is a relational database and everybody wants to use relational databases. Now I have that for you. So it was, even in the 80s, it was kind of the buzzword. Back then, relational was the buzzword and everybody tried to slap it on their product. And thankfully, COP defined like, what does the system need to do to be really relational? And thanks to that, all the relational databases we know today are kind of similar, even though there are minor variations and stuff. The general approach doesn't vary too much between these databases. So even back then, buzzwords were a big thing, and yeah, some people then tried to write their own databases. Obviously, that didn't go so well, especially if the spiky-haired boss tries to write a database and he doesn't know what that graph doesn't have the most RAM, but yeah. So, and then we kind of were in the 80s and we had this variety of databases, like the database world exploded. Everybody wrote their own database, there was a lot of innovation and stuff like that. And then we kind of fell into the dark age. The dark age looks something like this. Some people might agree or might not agree, but we had just a few very big vendors who bought up all the smaller ones and took over the market, and kind of innovation was not as intense anymore. Competition was not that big. If you were a company, you at some point selected a tool, for example Oracle, and from then on, every time you needed a database, you would select an Oracle database. You wouldn't care about the requirements or the cost or anything. You were mostly an Oracle shop and you would use Oracle. Same would be true for, if you ever met somebody from IBM, you would probably use DB2, IBM Java, and all the other crap nobody wants to use, but you would go down that route. Okay, and then, yeah, this was not good. Uncle Bob, who knows Uncle Bob? Yeah, most of you. He wrote a very nice blog post where he compares databases and beer, and he says like, in the US, when was the prohibition, like I think 20s or 30s, when alcohol was forbidden in the US, the Americans forgot how to properly brew beer because they were just not allowed and the knowledge was lost. And that is why they had such terrible beer for decades. And only recently, all these microbreweries came up and people started to brew proper beer again in the US. And he kind of compares it to databases. This is the same thing. Like in the 90s, the big vendors bought up everybody else, and while it was not forbidden to develop your own database, people just stopped doing it and kind of forgot how to properly build databases. And this was the dark age, and today we're hopefully out of that dark age again. So what kind of drove this getting out of the dark age? First, the argument against relational databases is often it's slow. So kind of think like, the dog is your application, would be way faster on its own, but there is this relational database as bottom, and the database just needs to write, the application just needs to write on your slow database, and it's super slow and inflexible, and yeah. So this is kind of the idea that many people thought, well, my application is held back by the slow relational database, so we need to find something else. So scaling is always nice. One more paper consistent, available, and partition-tolerant web services. That's basically the CAP theorem. Who has heard of the CAP theorem? A few, nearly half. Described by Gilbert and Lynch, where they say, okay, these are 3 attributes you want to have, but you can have at most 2 of them. Just to graphically picture it, these are the 3 qualities your distributed system wants to have, but you can at most pick 2 of them. So you can be either here, here, or here. You can never land in here. And if you design your system badly, you might end up here or even here. Like you don't have any qualities at all, depending on how badly you build them. What are these qualities? Consistency is at one point in time, assuming you have a distributed system. If you have a specific query, all the systems give you back the same answers. So this is kind of like timeline, and data changes over time. And at one specific point, you want to query your system and get from all the participants the same answer. If that holds true, your system is consistent, like it's a temporal view over your data. Do not mix this up with consistency in ACID, because there in ACID the consistency is actually moving from one consistent or valid state to another. So in ACID it would be you don't have any not null constraints violated. You have all the referenced keys are actually there and stuff like that. So in ACID it's more a predicate. Here it's a temporal constraint. The next one is availability. You have 5 nodes, and even if your network fails or whatever, you want to have all the reachable nodes should still respond to queries. It kind of makes sense. You don't want to waste any resources. All the reachable resources should be able to respond to your requests. And last one is kind of a given in a distributed system. If you have multiple computers, bad stuff can happen. And it's very hard to know, has a node died, or is it just slow, is it reachable, is it not reachable? But your system needs to be able to cope with that still. So partition tolerance, that your network can partition into 2 or more pieces, that is kind of a given. And depending on where you want to lean, you need to select which qualities you want to have and which quality you do not want to have. And if you have kids at home and you want to explain them what the CAP theorem is, you can also do that with the help of Robinson Crusoe, because I think Robinson Crusoe was English and he was stuck on his island, so he was kind of partitioned from the rest of the world. And then assume the ship comes by and asks him a kind of question like, who is the King of England? And then he needs to decide, am I available? And I answer, but my answer is probably outdated, then I'm not consistent. Or, am I consistent? Then I don't answer, because I don't know, maybe I don't know the actual answer. Then you're consistent if you don't answer, but you're not available, because you're being asked and you just say, not sure, cannot answer here. And there's this thing called eventual consistency, where systems will eventually keep or get the updates. Think of that like a message in a bottle. So every now and then he gets the bottle with, I don't know, a newspaper or something, and where there is written like, the King of England is that and that, then he knows, okay, like, I'm at most like half a year behind, and King of England was up to half a year ago was that. And there's kind of the same thing with the CAP theorem, that like the paper is actually super simple. Assume you have 3 nodes, like the network partitions between them, so on the one side you have 2 nodes, and on the other side you have 1 node. And you write data into your system, like you write data into the 2 nodes here, and they cannot propagate the update to the other side. And then some client asks that single node, what is the key, for example, that was updated here? And then that system again needs to decide, am I consistent? Then I don't answer. Or am I available? I'm answering with the best information I have, but that might not be consistent with the rest of the system. And this is a decision you need to make. If you do not make the decision yourself, random stuff will happen. And that is probably worse than making this decision explicitly. Okay, and then there are always the people who say, but my network is so stable and we host our own hardware or whatever. There's this guy called Kyle Kingsbury, be careful with his Twitter stream, it's pretty explicit. But he does great technical stuff as well. And he has this post, the network is reliable, and there he has documented all the stuff that can go wrong in networks. And he has, from Amazon, Microsoft, Google, etc., he found various stories, and he says like, On average, we lose that many blades a day, or that many routers, or that many racks, and this is all the stuff that has gone wrong because of human error, or hardware fault, or power surges, or whatever. So there's lots and lots and lots of stuff that can go wrong and will go wrong. Either you have been lucky, or your monitoring is just bad and you just didn't recognize that your stuff is broken. But your application will notice if stuff is broken, and if you have not made the decision explicitly, yeah, it's just random. Okay, and the second push that databases had was the schema flexibility. So, like, how could you structure data? The first choice is you have just bytes on physical storage. This is pretty much useless for databases. You just have bytes and you don't have any major information about that. The next thing would be you have key values, so like memcache key, Redis, whatever. You can just look up stuff by key and they point to a value and you can retrieve that value. But you can never search over that value. That is also already pretty different from relational databases. Like, you don't have an index, but you can still query one column. It might be slow, but you can always query every single bit of information you have in your database. That is not possible in a key value store. Then we have the advanced data structures, however you want to call them, where you have, for example, the graph databases, which are super good. You have nodes and relationships between them. And for example, you want to find the shortest path between two nodes. And it stores these relations in a very efficient fashion, so you can easily traverse the graph and find that nearest neighbor very easily. Whereas in relational databases, this is very hard. So for example, if you had a node and it has lots of relations, you need to go to all these relations. And then you need to go to all their relations. So your model really quickly explodes. So if you have a big system, that is not doable. You will need to do stuff like that in the graph store. Then we have the document stores, which store JSON. Since everything is JavaScript, JSON, yeah, it's kind of a given. XML is dead. I'm never sure if JSON is so much better than XML. We can argue about that later. But it's just okay. At the moment, we need to have JSON and we need to store JSON here. And then we have column-oriented family, which qualify data in families, and you can easily retrieve a single column. And what you often have is you don't only have a row and a column, so it's kind of two-dimensional. You often have a third dimension, like the time. So you have timestamp values, and you can actually get either the latest time or previous versions. So you have column, row, and the time, so it's kind of three-dimensional how you structure your data then. And then we have the relational world. And as you can already see, like stuff like joins is mostly, not exclusively, but mostly limited to the relational world. So while the other systems are also nice, this is something you will lose. This is kind of a trade-off. Okay, so NoSQL is actually not only SQL, not no as in nothing SQL. And some people say the name actually comes from this, like everybody knows these recruiters, they ask you like, do you have a specific skill? And they ask you, do you know SQL? And then you say no. And then your recruiter thinks about it, and then he sends out your CV and it says expert in NoSQL. Like, yeah, the general thing like recruiters might do. That is actually not true. Like NoSQL, I think the first time it came up, somebody, I think it was an Italian, he wrote a system that was relational on the inside but didn't expose an SQL interface. The product is long gone, but I think that was in the very early 2000s or something like that. The product is gone, but that was the first time NoSQL as a term came up. And then, like 2005, 2008, I don't know, something like that, there were all these new non-relational databases, and they organized a conference. I assume it was San Francisco, since everything is in San Francisco. And they came together and they needed a Twitter hashtag. And somebody came up with NoSQL because they didn't have SQL interfaces. Even though nowadays probably no rel or no relationships or something like that would be more fitting, but we're stuck with NoSQL. And also since there was no COTS 12 rules, these are very much less defined. Like there is not, NoSQL is a very broad term and you can stuff lots of stuff into it. Yeah, and of course everybody wants to use the latest stuff, and the evil boss, yeah, found, bless you. Big data, and big data lives in the cloud, according to the book of Wikipedia, and yeah, it makes you load much richer. Bless you. And yeah, so how does big data actually play into this? I think there are two definitions. The one is very broad, like big data is just everything that is a lot of data. Let's say a lot of data is everything that does not fit on your laptop, like you need to spread it out over multiple servers. Like if it fits on your laptop, it's not big data. Let's just stick to that, otherwise I'm getting very unhappy. And the other definition is narrower. It's more for offline data, data warehouses, everything you do with Hadoop and Spark. Stuff like that, that is like this data processing that is more big data. Like depending on who you talk to, it's either one of these definitions or just a general term they throw around to promote whatever idea they have. And I don't really like the term. I think it's kind of overrated, so don't say big data. It just doesn't mean anything. Okay, so this was the theory. Let's jump into some practice. There is dbengines.com. They have a ranking, depending on how much you believe them. It's like the programming language indexes like Tiober and stuff like that. They have their metrics. How good they are, we can always discuss, but they have a ranking. So it looks like this. This was a September ranking. Not sure if the October one is out yet. Oracle is still on top. We will take a look at Postgres, since it has overtaken MongoDB again. And it's also very much in fashion at the moment. We'll also take a look at MongoDB, since it's the most widely used NoSQL database. We'll take a quick look at Cassandra, Redis, and Elasticsearch, since these are kind of the most popular ones and sticking out.
Access is still there.
Yeah, I'm always wondering why Access even qualifies. Yeah, it is there, but I won't talk about it.
Well done.
Yeah, sorry. Okay, let's talk with MongoDB. Even though what I say about MongoDB is pretty much applicable to all the document stores, so you could use CouchDB. They have a release 2.0 now, I wouldn't have believed it. Couchbase, Elasticsearch, everything that stores JSON. Pretty much the same, I'm just picking MongoDB since they are most widely used. So, Ted Newell once said, or had a blog post, ORM is the Vietnam of computer science. I think the blog post was like 10 years ago, pretty much 10 years ago. And back then I think Hibernate just got started, so stuff was much worse back then. But he had like his theories and says like, either people are giving up on the relational world and just serialize data into it, and he has just multiple things that people would do that would totally break. And basically the idea is like, you have your nice object-oriented world, and then you have the relational world, and you have this impedance mismatch that the two just don't go together that well. And it's like putting a square thingy into a round thingy, and it just doesn't really fit. And this is kind of the general idea of the blog post. So, I don't know how many of you are Java programmers. Who has written something like this at some point in their life? Okay. So this is an M2N join, which you can actually access from both sides. So we are just having customers and dealers, and we just kind of need to match them up. And who thinks this is okay? Someone? Okay. Saying, I'm okay. You're either in denial or it's kind of Stockholm syndrome. Okay. Why is this probably not such a good idea? Let's just take a look at the impedance mismatch. So, for example, assume we have an abstract base class employee, and we have two specific implementations, managers and workers. And managers can approve funds, and workers have experience. Actually, or obviously, managers don't have any meaningful experience. So we want to implement this in a relational database, and we have three options in the relational world. First one would be a union table. So you have one employee table and you throw in all your stuff. With our two specific implementations and just one attribute each, that's kind of fine. But assume you have 5 implementations and you have lots of different attributes, then you will have loads of null values, which kind of works, but you can see it doesn't really play the full potentials. Also, you might want normally to have some constraints like not null or whatever constraints. With all the null values from the different specific implementations, you cannot really do that. So yes, you can store it in the relational world, but it's kind of a Swiss cheese and you have just null values all over. And it just doesn't fit that well. So alternatives would be, you just make concrete instances. So you have a worker table and a manager table, which works fine, you can query them independently. But what happens if you want to get all the employees, both workers and managers? Yes, you can totally do that. You can write a union clause and join the two together. But again, in the object-oriented world, this is super simple. You have just the object base class and then you operate on that and get all the thingies you have in it. But in a relational world, you need to join and it just like feels like it doesn't really match up. Third option would be you have a base table, like the employee, and then you have concrete instances, so you have worker and manager, you have 3 tables in total. If you just want to get the common attributes, you can query the base table. If you want to have a specific worker or manager, you would need to join the base table with that specific table. So again, you need to look in 2 places, you need to join data, it's just, whereas in the object-oriented world, it's just like the object and everything is in there, you don't need to do any joins. It feels kind of weird. So in MongoDB, you can simply do this. This uses Morphia. They call it ODM, Object Document Mapping. Since they don't have relations, they cannot call it ORM, they need to call it ODM. But it's kind of the same idea. You annotate your abstract class. You want to store it in it's called collection, but think of it as a table employee. And then we have an ID. And the specific implementations are just the same. And this is what we would store in the document store. It's just like pretty much the same we have in our object-oriented application. It's just like all the attributes that are there are stored. We know, okay, class name actually stores wherever that class name was, so we can actually say just give me the managers or just give me the workers. So this feels like a much more natural fit between the documents and the object-oriented world instead of just trying to push it into the relational world. Only 2 downsides is if you want to refactor your class names or your class path, you will need to change this as well. Or you could just skip this thing and just use an enumeration or something like that, just to make the difference between managers and workers. And the other thing that might look weird is the ID. While in relational world databases we have our nice sequential auto-incrementing ID. This doesn't look as nice, but this is because it needs to be, the generation of that should be distributed amongst servers or clients. Like this is not generated by one central instance, but this can be spread out over multiple instances, so you don't have this single point of failure and not this bottleneck of generating IDs, which is again kind of a trade-off. It's not as nice, but it works. The main downside of MongoDB is then, I would say, scaling. Some lady was running around here in the nice shirt, MongoDB's web scale, which is great. There was the thing where I think this was this computer animated thing that talked about how Mongo does not scale and stuff like that. And you can kind of see it here, like if you have just like, can keep your data on one server and just need to replicate it, this would be all you need. But if you need to spread your stuff over multiple servers, you have lots of moving parts. So assume you have so much data, you need to split it over 3 servers or so many queries. You need to split it over 3 servers, and then each of these needs to be replicated in case that node goes down. One of these 2 others can take over. And then you need 3 configuration servers, which actually tell the clients who have a router component to which server to go to query what data. So just to split your data over 3 nodes, E3, you actually have 9 servers down here, 3 down here. The routers normally live on the same server as your application servers, or behind a load balancer. So this adds lots of moving parts and overhead. So this is why people say this is kind of a pain to scale at some point. Okay, next up, Redis. Redis, key value store, and more. Who's actually using Redis? Okay, quite a few. Redis stands for Remote Dictionary Server. So it's not just key value, but it adds more data types like lists, sets, sorted sets, etc. And we'll quickly look at the use case of statistics. So assume you have a website and people log into your website. And the marketing team wants to know who. And Redis allows you to do that pretty easily. You have two data structures you can use, either bit sets or hyperlog. Bit sets are pretty simple, like your users are registered, and when they log in, like the first user you have ever registered gets the first bit. The second user that has ever registered gets the second bit, etc. So when the user logs in, you know, okay, this was the number he has signed up, so this is the bit that belongs to him. And if he logs in, you just flip this bit from 0 to 1, he has logged in. So for 1 million users, you will need something like 123 whatever kilobytes per time frame you want to collect. So for each hour, you would need 123 kilobytes, so a day would probably be like 3 megabytes or whatever. That should be pretty simple. If you have way more users, you might need to use something different, but most services should be pretty fine. And this is super simple. It's just like 1 bit for each user, and you can simply flip it on or off depending on if they have logged in or not. And then there is hyperlog. Hyperlog is only probabilistic, so it just needs 12 kilobytes to store loads of unique elements. The downside is there is an error rate, which is like at 99% of the times you know the specific user has logged in if you query that data structure, but you cannot be sure 100% of the time. But it needs constant space, so in 12 kilobyte you have everything covered. Yeah, that's the documentation if you want to go more into hyperlog. There is also a paper how it actually works internally, and it's just like you're meshing together different attributes, and it's very likely that with the specific bits that have been flipped, you will actually be able to tell like, has this user logged in or has he not logged in. So, comparison, hyperlog is nice because it has constant size, it doesn't grow anymore. Bit sets are nice because they're exact. That is often what your marketing team says it really wants, because they don't want to be 99% sure somebody has logged in, but they want to be really sure somebody has logged in. And the other thing is, it is very easy to aggregate. So you have for a day, if you do it by hour, you just have your 24 bit sets, and if after a month you say, I don't care about the specific hour, I just want to know has this user logged in during the entire day, you simply or connect all the 24 bits belonging to one user, and if he has logged in any of the hours, you will get the 1, otherwise 0, and then you will just know he has logged in during that day or not during that day. So that is very easy to aggregate. Yeah, overall Redis is super simple. It's kind of the omnipresent glue. It's just like scalability is not like its main thing. One very common approach is that you actually shard it on the client side. So your client application knows, okay, the key space from A to C goes to that server, D to F goes to that server, etc. Yeah, I know there is a clustering component now, but it has been more recent than the rest of the stuff, and I'm still not sure like how many people are actually using it. Some people have written their own proxies to try to take care of that and know where which key is stored, like Twitter. So scalability is kind of a big issue there. Okay, next up, Cassandra. Cassandra actually makes fun of Oracle, because you know in Greek history, Cassandra, I think that she was one of the inhabitants of the city of Troy, and she saw the future, and she wanted to warn the other inhabitants, and then I think it was the snakes who came to kill her or something like that. So she saw the future, but nobody believed her, whereas the Oracle of Delphi, they didn't know anything. They would just sit in their whatever fumes and have hallucinations, and they didn't know anything. So this is kind of their take on the name, that people from Cassandra see the future, whereas the Oracle has no idea what they're doing. So what Cassandra is really good at is scalability and high availability using consistent hashing. So we'll quickly look into what consistent hashing is and how it works. This is a bit small, we'll just jump into each of these parts, but this is kind of the overview. So first off, every entry you want to store has a key, and you take the key and you hash the key, and you have your total key space, and depending on where your hash key lands, you just split it. If you have 3 servers, for example, you just split it into 3 even chunks, and then you hash it, and it will land here, so it will end up on the key range B.
and you have A and C as well. Any ideas why I would want to hash my key and not store it directly? Because I could simply say, okay, my key Y is, I don't know, here, and I simply will store it here. Why am I going through my hash function? Why do I add this overhead? Sorry?
When you have this to the server.
Yeah, the problem is if you generate this key here and the key is not evenly distributed, you might end up with hotspots. So, for example, if you would use, I don't know, the last name or whatever, probably I don't know, is E the most common letter in Spanish? A? Okay, in English and German, E is the most common letter, for example. So you would end up with lots of entries starting with E, but for example, Q or something like that, there would be very few entries. And just to spread out your keys evenly over your entire key space, you throw it through the hash function. If the hash function is good, your data should be very evenly distributed over all your nodes. Next step is you rotate your key space clockwise. So you just rotate it to have a circle, and then if you hash a value, for example X, it might end up on the server A. And then you also replicate the data to the next server. So hash X lands here, which goes further down, okay, it ends up on the server A. And additionally, you also copy the data to the next server, to B, just to have an additional copy instead, in case A fails. And you hash Y, and Y ends up on B. And yeah, that is also copied to C. And that ring is like not the topology, it's not like a token ring network, and your servers need to be in a token ring network and they need to look like that. This is just the mental model and how data is distributed. So just how the data is distributed is this ring you're using. It's not anything physical. And the nice attribute of this is if you add another node, for example D, you could simply say, okay, I'm splitting up A into two key spaces, and A just needs to hand over half of its keys to D, and then okay, you will factor out the replication and everything, but it's just like you just add a node here and it doesn't affect your entire system. Or if you remove a node, or if a node fails, for example B fails, then C says, okay, I will take over the key space. Since I have the copies of B already, it has been replicated to C, it will just take that over, and then it knows, okay, since B is not coming back within a certain time, I need to replicate my data again, just to have a second copy, and it will replicate the data to A. So that is just sticking to that model. And what you normally do is, it's called vnode for virtual nodes. You will not make one big chunk for each server, but you will split it up into more smaller ones, and then you have multiple copies on all the servers distributed. So if one of the servers dies, it's not like big chunk fails, but like many smaller chunks that are distributed over all your nodes might need to be replicated. Or if you add a server, you just take out like bits and pieces like these three, for example, which relate to the three key spaces, can be put to that server. So you have it spread out more evenly and not just like a single server needs to take all the load. Yeah, downside is, like your father might have warned you, consistency is something many people expect, and normally Cassandra does not expose consistent behavior unless you use read and write quorums, which means actually whenever, so assume you have your data is kept 3 times. So the write quorum would mean before you successfully return the write, it needs to be like acknowledged by at least 2 of these servers. And to read, you would need to read from at least 2 of these servers to have a consistent read. So if you always write and read to the majority, you will know you have a consistent state. But of course, it has the additional overhead that you need to write to at least 2 of them before you can acknowledge the write, and you will need to read from 2 servers every time you want to read a single value. So many people are not doing it, and Cassandra is there for, yeah, often eventually consistent. But where Cassandra is really impressive is in the number of services it can use. I think Apple recently released some numbers, and they have a cluster with more than 1,000 nodes in a single cluster. And I wonder like how many queries that thing is doing. Like why do you need that many nodes? But they have a cluster with more than 1,000 nodes and like tens of thousands of Cassandra nodes in general, I think. Okay. And yeah, the relational world is often not very happy about this eventual consistency, and they say eventual consistency is basically a lie. It's only immediately inaccurate. This is kind of the idea of what eventual consistency is giving you. Okay, Postgres. The elephant is getting more and more popular. That is probably too small. I will try to act it out again. So one guy says, our relational database is way too slow, we need something else. And I've looked into NoSQL alternatives, and I've made a 3-month battle plan. And I've created a Gantt chart, like this is how we will do the migration, and we'll spend 3 months on rewriting all the queries from the relational world to the NoSQL world. And then the colleague says like, wait, let me check. And then he checks and says, oh, just as I thought, you have forgotten to set the right index. I have added the index, and now your query is 100 times faster. And we're still good enough with the relational world. This always keep in mind, if you set indexes and set them correctly in the relational world, this is not percentages you talk about, but normally really factors. Like if you have lots of data, you will improve the performance by 10x or 100x or whatever. It's not just 100%. So often for many workloads, relational databases, if tuned correctly, are totally fine. Of course, you can also do it with NoSQL because you probably want to play around with that. But like from the business case, it is not always required. And also like relational databases are not just relational anymore. SQL in the latest standards has evolved a bit further. And that's why many people try to call them SQL databases now, because SQL is kind of their defining factor. And the SQL standard is pretty big. If you're not on MySQL, you can use most of the features the standard provides. MySQL is always a bit behind with the features. But yeah, advanced SQL features are powerful, stuff like windowing functions and that. So it's not only about the relational model, but the SQL model can do lots of stuff. And because SQL is so popular, lots of other companies in the NoSQL space, who are actually called NoSQL products, are adding SQL-like interfaces, which I find kind of amusing. So Cassandra has their SQL, the Cassandra query language. Google has their Google query language. Couchbase was a bit more creative with its name. It's called Nickel, but it's kind of the same thing. Rethink and lots of other databases, they all have their SQL-like interfaces. Some are treacherous, like I would say the Cassandra query language, at first sight, the P is kind of close, but once you want to use any slightly more advanced SQL query, you will miserably fail, because in the background, it is just not a relational database. It's just like bolting on top like a very thin layer of SQL-like syntax, just to feel more at home in the beginning and fail miserably afterwards, but that is the approach Cassandra kind of used. Whereas Couchbase, for example, I think, what was the SQL standard? I think it's 92, and they are very proud that they support SQL 92 and of course more stuff, because they're a document store and need more stuff. But the relational people then always make fun and saying like, I'm SQL 92 compliant, would be like advertising your application as say, I'm Windows 3.1 compliant, because Windows 3.1 also came out in 92. And nobody would advertise their application as Windows 3.1 compliant, right? But the relational, the NoSQL people still say, oh, we're SQL 92 compliant. Yeah, and what you can see is features and maturity from the relational world, and they also have the NoSQL influence. Like Postgres supports its JSONB data type. MySQL has also some JSON support, and just like lots of the features that the non-relational world has pushed forward is kind of being picked up in the relational world now. Okay, to conclude, or like final product, Elasticsearch. This is actually full text search and not a relational database.
So I always compare it to being like very much black and white. Like relational databases are black and white. You query something, you have an exact match, you get that result back. Whereas full text search is more fuzzy, shades of gray. Like you search for a term and you do not care about is it singular, is it plural, is it an adjective, is it a noun. I'm looking more for a concept, and that is what full text search gives you. So what it normally does is you have some document you want to search. First step would be remove formatting and properties. Then parse the entire thing. Parsing would be like find the independent words. It's like split up spaces, punctuation marks, stuff like that to find the independent words. Remove stop words. Stop words are very common words. It's A and D, my, whatever. These little words that add very little meaning because they're in every document anyway. Just remove them because they don't help you, they're everywhere anyway. Do stemming. Stemming is just removing the word ending. Is, for example, lazy or laziness or whatever would be stemmed down to lazy with an I at the end. It's just like remove the word ending and get it down to the word root or stem. Depending on the language, in French you might need to remove something at the beginning. In German you would need to purge the umlauts and also do something with the ending. So this is very language dependent. But just reduce the word down to its root or just generic form so you can find everything that is related to that term. And you might have synonyms. That is very use case dependent. Maybe you have synonyms in your documents. And then you have your index. So how this would look like an example, you have the bright blue butterfly hangs on the breeze and two other documents. You remove the stop words from these documents and then you say, okay, I have these terms, like you have extracted all the terms, like best, blue, bright, whatever, and you say, okay, these appear in these documents. And then you could, for example, query like, if I look for blue sky, blue appears in the documents 1 and 3, and sky appears in the documents 2 and 3. So if I look for blue sky, only the document 3 has both of them, whereas blue is in 1 and sky is in 2, but I don't care about one of them, I just need the combination. And this is kind of what full text search does. It's just like stem down to the word stem, have this big list of all the independent words, and then you can search for one word or the combination of words. And the last thing is then you normally have a score or a quality if you search for terms, and there are multiple things coming into play. This can get a little tricky. Like something is normally the term frequency. The more often a specific term appears in one document, the more relevant the term that document is. So if you search for sky, and one document contains sky 5 times, and another document the term sky 3 times, having sky 5 times makes the document more important than the one 3 times. Or if you search for multiple terms, more common terms are probably less important. So if you search for dog and rover, dog will appear in lots of documents, but rover is probably only appearing in very few documents. So documents containing rover are therefore more relevant than just dog, because the less common term is probably more meaningful in your search query. And the other thing that often plays into it is field length. The shorter a field and the word appears, the more relevant it is. So if you have a title with just like 5 words, any match in the title is more relevant than the text body with 1,000 words, for example. Like these are kind of the general ideas how to actually score and rank words and terms. And I don't know who is using what was called the Elk stack, now the Elastic stack. Good. Yeah, we're not only doing full text search, we have the visualization in Kibana. We ingest data with Logstash, we have our lightweight agents. So this is kind of our entire stack. Yeah, to conclude, like back in the 70s there was no SQL at all. In the 80s it was, yeah, you should know SQL, this is the thing to use. In the 2000s it was no SQL, like SQL this is too slow, we don't want to have that. Then it was not only SQL, SQL is fine, but sometimes you need something else as an alternative to that. And now, depending on who you ask, some people say no, this whole no SQL thing has failed, and it should be just SQL again.
I would see this a little different. I think like both the relational world and the non-relational world, both are around to stay. Depending on your use case, you can use either one of them or the right combination, and you just need to find the right mix. By the way, I have at the very end, I have the reference. I have not created this one. This is very common on the internet. And then there's always this question, but is it fast? Like, which is the fastest database? And this is my favorite slide here. You have Professor Sipkinski, who tried, is the cat more intelligent than the squid? And he tested them under similar conditions. And obviously, the squid is much more intelligent because the squid is still doing the puzzle, whereas the house cat is dead. So the house cat is much more stupid. And pretty much the same is true for all these benchmarks. I think like 1.5 years ago or so, MongoDB, Cassandra, and Couchbase, all three did benchmarks with their two competitors. And each one of them managed to be at least twice as fast as the other two. But each one of them. So it's just like finding the right combination of one server, multiple servers, you use for your competition use some bad parameters or an old client or whatever you need to find. But like all these public benchmarks you will find are probably mostly crap. You will unfortunately need to benchmark for yourself. And yeah, that's the last slide. Go through, find which database you should use. And this is actually a few years old already because I think FlockDB is not around anymore. HBase is also not that widely used as a data store anymore. But yeah, you can go through. Now I'm just interested in where you end up. Okay, who is with Google or Facebook? Who ended up at HBase? Nobody. FlockDB? Flock? Nobody Flock? Neo4j? Okay. Right? No? Couch? One. Mongo? Relational world? Good or relational world? Okay, thanks. I've got lots of stickers here. Grab some swag so I don't need to carry it home. Thank you. Try to keep it light so you don't fall asleep. And then we'll dive into a few specific database systems. Okay, so let's get down to the databases. What are databases and how did we get here basically? Like the classical paper is a relational model of data for larger data banks by Cod from I think 1970, which kind of founded how we see databases today. Like before that, you had different implementations of databases and everybody had their very own implementation, and if you wanted to interact with that, your application had to be just geared towards that database very specifically. So you couldn't switch anything, you really needed to know like how does this database work internally just to make use of it in an efficient fashion. And Cod said, well, this is stupid. Let's find something more intelligent. I will just generate a generic model like just the mathematical abstraction, and everybody can then use that, and then all the systems are kind of abstracted away, and nobody does need to care about these internals of the databases, which sounds very reasonable. And what Cod in the end gave us is a relational model and normal form, which led to the data independence. So you just have this mathematical model as the underlying, could just write very simple SQL queries and get very powerful data back. Before that, you had to write your own programs and do complicated stuff. This made it much simpler. Like you have these aggregated reports where you can just do group by, sum, average, whatever. But what untrained users or even trained users are not so good at are normally stuff like concurrency, integrity, and stuff like that. That is why relational databases take care of that for you, and you don't need to care about that because that's also handled internally. And one other very nice thing Cod did was he wrote another paper, which he called Cod's 12 rules, which were actually 13 rules because like every good person in IT started counting at 0 and then went down to 12. And there he defined what are the rules, or what does the database need to do if it wants to be called a relational database, because like there were all these vendors who had products out previously, and they would just add a tiny little feature to their database from the relational model, and then say, oh, this is a relational database, and everybody wants to use relational databases,
Now I have that for you. So it was, even in the 80s, it was kind of the buzzword. Back then, relational was the buzzword, and everybody tried to slap it on their product. And thankfully, Cobb defined like, what does a system need to do to be really relational? I'm Philip. I talk about databases. Yeah, thanks to sponsors for making the event possible. And as I've already been asked, I'm from Vienna. I'm always describing it like I'm from Vienna, a city of fatty foods, classical architecture, and beautiful women. No, we love Conchita. Finally, we won the Eurovision contest with her. Yeah. I'm at Elastic. I'm part of the infrastructure team, so we do everything like testing with Jenkins, AWS instances, Ansible Chef, publish scripts. And this here is a pipe, and I kind of pipe my infrastructure work into developer advocacy. So I'm out in London at conferences and meetups just to talk about our stuff and other stuff I find interesting. And when I'm not running around somewhere in the world, back at home I always also run meetups. One about databases in general, and the other one about papers. We meet once a month and talk about one classical computer paper. Sometimes distributed systems, sometimes old languages. We had just like Perl and Prolog and whatever, how different languages developed and stuff like that. Now we're more into machine learning. And this talk is kind of the combination of these two. So we'll start off with some theory, idea, and everybody implements that, and that leads to some kind of data independence. You don't need to know how is the data actually stored and organized internally. You're just relying on the mathematical model. And what Cod did was this here. If you can read it, this is what we would use today, select name from people where dialect is null, so all the people that are still alive. This is not what Cod did. Cod did this. He created just a mathematical idea, and I guess most of us are pretty glad we don't need to interact with that. So he says we have a free variable name t with an attribute name, and there exists a tuple name and dialect age where this x that exists is in the sum of people, and the x dialect age is empty, and the t name matches that x, and that can kind of translate it down to that. So this is basically what Cod did. It was just a mathematical idea in the background how to interact with that. And then also IBM guys came up with SQL, a structured English theory language, by Boyce and God. Definitely a Boyce. And you can see this was SQL. Today we just have SQL because somebody else had the trademark on SQL. And they started with it, and then the company having the trademark complained, and then they said, well, we'll just remove a few letters. And afterwards it was then called, yeah, SQL, yeah. The acronym, actually, the SQL was first, and then it was just stripped down to SQL. Yeah, and what that guy gave us is that is kind of declarative. We do not need to know how this works internally. We just tell it like, these are the rules and I want the stuff. That is how do you do that internally? I don't care. I don't care if this is a loop like for, while, do loop, I don't care. Just these are the rules, give me data fitting those rules. And the internals are then part of the query optimizers. So you do not need to know how MySQL does the SQL Server, Postgres, whatever. You don't care. That is thanks to Cod's abstraction layer, that all of them behave kind of the same way. And you can also see this was already made for user interaction. Like you have aggregated reports back in the 80s when the relational databases started to come up. This was kind of a new thing that even untrained people